Hi, thanks for joining me. Today I've got a fun problem for you. What we're going to do is consider this 5x5 grid, and we're going to add some dominoes onto this grid. And what we're going to do is add some dominoes, so perhaps our first domino could be there, our second one could be there, and so on. We're going to keep adding these dominoes. It doesn't matter how we do them, but there is a rule, and that rule is we can't leave any spaces for a further domino to be added. So if perhaps our setup was like this, we wouldn't be able to stop here because we can see we could still fit another domino there. So we'd have to continue and add on that domino there. But now we can see that there's no way to add another domino to our grid. And now when you do this, you might leave some holes behind. In this case, we do. We leave this guy, and this guy. So there are 3 holes remaining. The question is, what is the maximum number of holes we can leave behind? So in this particular arrangement of dominoes, we leave 3 holes behind, but if we choose a different arrangement of dominoes, we might leave more holes behind. So the question is, what is the maximum number of holes we can leave behind? So essentially, we're not allowed to have 2 holes adjacent to one another, because otherwise we could fill those 2 squares with a domino. Okay, if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so it turns out that the answer is in fact 7. So 7 is the maximum number of holes we can leave behind. So this is one example of a particular arrangement of dominoes which allows for this. So if we have the dominoes added to our chessboard like this, we can see we've got 1, 2, 3, 4, 5, 6, 7 holes there, and there are no more, no less, and there's no other place for us to have put a domino. So this is a valid solution. So this gives us 7, but I claim that 7 is the maximum number, so we can't choose any or arrange the dominoes in another way, which gives us a greater number of holes. And now let's see why. So let's firstly clear up our grid, because now we know that it is possible to do it with 7. We now want to prove that it's impossible to do it with more. So what we're firstly going to do is think of our grid as a part of a chessboard. So we're going to colour in the squares and alternate going from one to the next. So we'll have white, then black, then white, then black, and so on. So we'll get a chessboard arrangement like this. And I probably should mention that this is kind of a very standard technique when dealing with these sorts of problems where you're adding dominoes to a grid, is to think of it as a chessboard. And here's the reason why. When you add dominoes to this chessboard, so let's just choose an arbitrary domino, let's say 1 here, we notice that the domino covers 1 black square and 1 white square. And this applies no matter where you place the domino. It's always going to cover 1 white square and 1 black square. And so firstly, in particular, each domino covers 2 squares. And so because the total number of squares here is 5 times 5, which is 25, if we subtract off the numbers of squares which are covered by dominoes, well, we know that that's going to be 2 times the number of dominoes, so an even number. So we've got 25 minus an even number gives us the number of holes. So that must mean that the number of holes is an odd number. So h is odd if h represents the number of holes. And so if we're supposing if we suppose for contradiction it's possible to do it with more than 7 holes, that must mean that h is at least 9. So we're supposing that the answer is 7, or that's what I'm trying to prove. So to prove that, I'm going to suppose for contradiction that it's possible to do it with more holes. So because the number of holes has to be an odd number, that would suggest that it's possible to do it with at least 9 holes. So that's what I'm going to try and prove is impossible, so arriving at a contradiction. Well, what we can do is also note that because each domino takes up 1 black square and 1 white square, that means that the number of holes, if we think of this, if this was a hole, that would be a white hole because it's a white square on our chess grid. But if this was a hole, that would be a black hole on our chess grid. Because there's 1 more white square as is at the moment than black squares, because we've got 12 black squares, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 is 10, 11, 12 black squares, and therefore 13 white squares. There's currently 1 more black square than, 1 more white square than black square, and when we add on the dominoes, that's just going to subtract 1 from both of those numbers. So therefore we have that the number of white holes, HW, is going to be the number of black holes plus 1. So there's 1 more white hole than black hole, and we have this equation here. So we're going to prove that it's impossible for us to do this. So it essentially have at least 9 holes. So let me clean up the whiteboard and we'll prove this. Okay, so we're supposing that it's possible to do it with at least 9 holes, and that I claim that we must therefore have that this central square here must be a hole. Well, why is that true? Well, we know that there are supposedly 9 holes in this 5x5 chessboard, so once we've added our dominoes in such a way that there's 9 holes. Now, if this central square wasn't a hole, well, if we look at these kind of 2x3 regions, there are 4 of them. This one, this one, this one, and this one. So there's 4 of those regions, and if this middle guy isn't a hole, that means that the 9 holes are distributed amongst these 4 regions. But then by the pigeonhole principle, at least one of these 2x3 regions must have at least 3 holes, because otherwise, if they all had at most 2 holes, you'd have at most 2 holes, at most 2 holes, at most 2 holes, at most 2 holes. That's only at most 8 holes, which wouldn't give us the at least 9 that we need. So one of these regions has 3 holes, supposedly, but that's not possible. It's not possible to have a region with 3 holes. Why is that? Well, let's focus on this one here, for example, and obviously just by rotational symmetry, this argument will apply to each one. Let's suppose it was possible to have 3 holes. Where are those holes going? Well, they certainly all can't go in one line, because then otherwise we could have added a domino there. So that's not possible. So we can't have them all in one line. So that must mean we have 2 in one line and 1 in the other. So let's suppose we have 2 in the top line, for example. So 1 there and 1 there, because obviously they can't be adjacent. And then we know we have 1 hole in this bottom line. And it can't go here, because then you'd have 2 adjacent holes, which is not possible, because you could have then added a domino there. So we must have that the third hole goes here. Now, why is this not possible? Well, then all of a sudden this guy here, well, it's not allowed to be a hole, because if it was, then you would have added a domino there, for example. But equally, it can't be part of a domino, because where's the second cell? We know that each domino must consist of a black square and a white square, but if these 3 guys are holes, there's no place to put the white square part of it. So this leads to a contradiction. And the same thing would happen, or a very similar argument would be the case when you have something like this. So these 3 guys here as your holes, then these 3 parts would have to be dominoes, but then how would this guy be a domino, for example? Okay, cool. So that means that the central square must be a hole. So let's put that in there. So these circles here represent the hole. So we've got a white hole in the middle. And then we know that in these 4 regions here, we must have a total of 4 black holes and a total of 4 white holes. Well, firstly, straight away, what can we say about each of these squares here? Well, they must contain a domino. Why is that? Because if any of them contained a hole, say this one, then we'd have 2 adjacent holes, which is not allowed, because we could have then added a domino there. So each of these guys here must be part of a domino. So maybe let's add that on in, let's go yellow. So yellow here represents part of the domino. So that there is a domino, or part of a domino, that's part of a domino, that's part of a domino, and that's part of a domino, and we've got a white hole in the middle. So we now know that out of what's left, we need to have 4, or at least 4 white holes and at least 4 black holes. And I want to prove that that's impossible. Okay, so we know that we're going to have at least 4 black holes and at least 5 white holes. Well, let's look at these 2x3 regions we have scattered about. Well, we have 4 of them, and now I claim that each of them must have exactly 1 black hole in. Why is that true? Well, firstly, they can only have at most 1 black hole in. Why is that true? Let's pick on this particular 2x3 region. Let's suppose it had 2 black holes, then they'd have to be there and there. But then the issue is what goes in this corner here. Well, because it can't be part of a domino, because if it was part of a domino, remember each domino needs a white square and a black square, but that's obviously impossible if both of these are holes. Where's the black square part of this domino? So that would mean this is not part of a domino, therefore a hole, but then you have 2 adjacent holes here, for example, and that's not allowed because you could have put a domino there. So you're not allowed to have 2 black holes in any particular 2x3 region. So that must mean that each one has at most 1 black hole in, but we know we need a total of at least 4 black holes, so that means each of these 4 regions here must have exactly 1 black hole in. So each of these 2x3 regions has exactly one black hole in, so we know that the number of black holes HB is going to be 4, and therefore the number of white holes HW is going to be 5. Okay, well, why does this lead to a contradiction? Well, let's focus on again on this 2x3 region. Where does the black hole go? Let's suppose it goes here. Okay, so we put the black hole here. Now the question is, where? Well, what are these three guys here? None of those three can be holes, because then otherwise you're going to get two adjacent holes, and that's not allowed because of course you could have put a domino there. So that means that each of these guys must be part of a domino. So maybe if I shade them in yellow like we've done before. So each of these guys here would be part of a domino, which is fine, for now at least. But the question is, we still need to have 5 white holes in our diagram. Well, we've got 1 here, and well, we still need 4 more, and we've got 3 regions left to look in. And so that means that at least one of these regions is going to have 2 white holes in. Now, why is this an issue? Well, let's say it's this region here has 2 white holes in, so this guy here. Why is this an issue? Well, that means if we have 2 white holes in here, that means there's going to be at least 1 white hole in either one of these 2 guys. So we could hide one of the white holes here, but we're still going to have to put one of the remaining white holes. So there's 2 white holes in this 2x3 grid. We put one of them there. There's still going to be at least 1 more. It's going to go here or here. It doesn't matter. Either of these, they're both adjacent to one of these, or in fact both of these. And so one of these will be a white hole, let's say this one. And we also know one of these is going to be a black hole, let's say this one. And why is this an issue? You get this guy here. And similarly, if this was a hole instead, you get that guy there. Either way, you're going to have something that you're not allowed, which is 2 adjacent holes. So that means, if you just rewind what we've done, that means that this guy here, this cell, can never be a black hole. So this the one that's in the middle, cannot be a black hole. So that means this can't be a black hole, so this one must be. So if I just clean this up a little bit. Oh, I've put a lot of dots into this. So yeah, that can't be a black hole, therefore this must be the black hole. And just by rotational symmetry, this will be the black hole, this one here will be the black hole, and this one here will be the black hole. But now, this is an issue, because, well, where does the white hole go? Because again, we need a white hole in each of these here. So where can we put a single white hole in this diagram? We can't put one here, because then we get 2 adjacent holes. We can't put one here, there'd be 2 adjacent holes. We can't put one here, there'd be 2 adjacent holes. Here, here, here. In fact, there's nowhere we can put any more white holes, and we need at least 4 more white holes. So that's completely impossible. And so we've finally arrived at a contradiction. So it's impossible to do more than, or at least 9 holes. And because it has to be an odd number, we know that it's at most 7. And we showed earlier it's possible to add the dominoes in such a way that you have 7 holes. So this proves the maximum number of holes you can get is 7. I hope you have enjoyed this solution. It's a fun little problem with a nice little bit of logic at the end. See if you can generalize this. What happens if you look at a slightly larger chessboard? But anyway, thank you for watching this solution video. I will catch you on the next one. Have a great day.